In this video, I'm going to talk about the molecular orbitals for ammonia and then for boron trifluoride, which are two larger molecules that are no longer linear. And so the process is essentially the same. So the first thing we want to do is figure out the point group for ammonia, which is C3V. And so we can see it has this C3 rotation here, and it has these three different reflection planes here. In C3, there's two of them because you have to do one and then two before you get back to the starting position. And so this is the C3V character table right here, and a reducible representation. So if we sort of put a coordinate on each of the hydrogen atoms, obviously if you do the identity, they all stay in the same place, and so the matrix for that is just going to be the identity matrix, and that will just be the character of that will just be the trace of it, which is just ones down the diagonal. If we do a C3, we can see that all three of the hydrogens change place, and so that will be 0. And if we do a reflection, so any reflection is going to change two of the hydrogens while leaving the other one the same, and so that is a 1. And so the two irreducible representations that generate this are the E and the A1. And so this, I put E here, but that should actually be a 2. I'll change that in the lecture notes. So that should be a 2. So 2 plus 1 is 3. Then, yeah, so I think I moved this over. So this should be the -1 right there, and this should have a 0 right here. So it should be 2, then -1, then 0 right there. And I'll change that in the lecture notes. But anyway, so it's an A1 plus an E here. And so this gives us the hydrogen group orbitals. So in these little formula right here, I'll actually explain where those come from in a couple videos from now when I actually get into the projection operator and sort of how to find these things. But for now, we can just sort of we'll just sort of accept that the A1, so the 3 hydrogen s orbitals look like this with the A1 symmetry. And in the E, we have these two things right here. So these are the two bases for the E symmetry here. So we have for the first one here has a single node, and so the node goes between the two white ones, and then the dark one here, there's a node between those, because you can sort of think about it like the two white ones are, sort of like this positive part of the wave function here, and then when we go to the other one, it's this negative part. So there's this area between them where it will be 0, and so that is a node where it goes from the positive to the negative. Then this HB minus HC also has a node that sort of goes between them there, and so when we do just the identity operation, they stay the same. If we do a C3 rotation, we see that this will rotate right there. We see that this sort of rotates, so it's sort of pointing out of the screen, and this one sort of into the screen like that. And if we do a reflection across here, we see that this top one stays the same, but this one down here sort of flips around. And so the characters for these, so we have the 2 here, we have the -1, and we have the 0. The way I like to think about it is we're sort of saying that this top one here is sort of like a 1, and this bottom one here is sort of like a 1. And then so if we change this around so that it's rotated, then this becomes sort of a like a 0, and this one down here becomes like a -1. Then up here we have this where it stays the same, so that's a 1, and this down here becomes like a -1, and so 1 plus -1 is 0. And we can look at the same thing here for the p orbitals. So the E symmetry here encompasses both the px and the py, and so we have this up here and this down here, so those are sort of perpendicular to each other, and we can do a rotation, well, a 120-degree rotation, so this dark part will sort of get flipped pointing out of the screen, this light part sort of flipped pointing into the screen. This -1 here sort of gets moved around so that this is sort of pointing sort of obliquely out of the screen and this sort of obliquely into the screen. Then a reflection will obviously flip this dark and this light one here, so it's a reflection sort of, sort of along a line like that, and it's flipping the dark and light one there, but it leaves these ones the same, and so that is a 0 there. Then we have our A1 symmetries, which are the PZ and the S orbitals. So we see if we sort of rotate or reflect through any of these, that these will just stay the same. And so it's just the perfectly symmetric representation here. So it's just all ones. So the A1 group orbital for hydrogen with the A1 atomic orbitals of nitrogen, so that's the S and the PZ. These will thus have the molecular orbital that looks like this. And so once again, this 1 over square root of 3, I'll talk about where that comes from in a couple of videos from now when I get into the projection operators and going through that process. But for now, that's just it's a normalization factor, and so we see that this is multiplied by our phi 1 plus phi 2 plus phi 3, or the phi for the HA, the phi for the HB, and the phi for the HC. And for the E symmetries, we just have these two. So this has the 2 phi HA minus phi HB minus phi HC. And so that is just these things up here. So this is the plus version. This is the 2HA minus HB minus HC. And we have the HB minus HC right there. And that is this one right there. And so we see how the normalization works where the fractions, so if we take this one right here, and so we multiply it by this phi HA here, which has a 2 next to it, so that's 2 over the square root of 6, and then we square that because, as we'll see in the upcoming videos, this squaring is because we want to sort of take the integral of the sort of phi 1, and then we'll have our Hamiltonian there, and then the phi 1. So this will actually be the star. And so we're actually multiplying these by each other, and so that's why it's squared here. So that gives us the 4 over 6. And for the HB and HC, we have the 1 over 6 squared and the 1 over 2 squared. And so we end up with another 2 over 3. And so then the contribution of each of those to the A1 group orbital is the 1 over square root of 3, and then we square that, and so that's 1/3. And so then the 2/3 plus 1/3 is equal to 1. That accounts for the 100% of the contribution. And so yeah, we see that these that this 1 over 6 here, so it's times this 2 here when we are talking about the HA right there, and so the HA doesn't show up in here, so it doesn't get this, it doesn't add to this 1 over square root of 2, so that's just the 2/3 there. Then these 1 over square root of 6, we get that here for the HB and for the HC. So 1 over square root of 2 is here for the HB and for the HC, and these negatives just go away because we're squaring, and so those just become positive, and so that's where all of those come from. So I'm actually going to start at the bottom here for these bonding orbitals. So we see if we have this node that goes, well, it's actually the node that goes down across here, which I talked about above, and then we have a node that goes across here. And so we see how when we add this to the px orbital or the py orbital, that we get this overlap, and then here we get this overlap, and then these overlaps going on here. And so that is the 1e bonding. Then when we have no nodes here, we have the s orbital like this and the z orbital like this. So we add those together and we get this, and we see how we have overlap going on between all those, and that's the 2A1. And we actually have the PZ here is actually partially or mostly non-bonding, which we will see in the molecular orbital diagram. And then the non-bonding ones, we have the node going there, we have the node going there, but now we see we have the PX and PY sort of, you know, canceling each other out in these ones where we have the phases in the wrong direction here. Then sort of the same thing for the 4A1. We have this S here and this Z here, and we have the wrong phases on there. So the nitrogen 2s and 2pz combine with the hydrogen A1 group orbitals of the hydrogens, which is what we see going on right here. So this is this right here are the hydrogen 2s and the 2pz orbitals, and then the nitrogen 2px and 2py are these ones up here. So the 2px and the 2py here with these hydrogen s orbitals right there. And so that's the E group that has the two nodes there for the hydrogens. So this is our molecular orbital diagram for it. And so this is kind of a slightly poor quality diagram, but I liked it because it showed how all of these orbitals look. So we can see here the hydrogen group orbitals, and so this is the one that has the node going between the sort of dark and light, which are the opposite signs here. This is the node that kind of goes between those right there. So we have the two light and then the dark there. Then we have this, which is the sort of perfectly symmetric node there. And so we see how these are overlapping with these nitrogen orbitals right here. And so what we end up with, so we have the A1 orbitals right here. So these A1 orbitals here are coming from this right here, and then this S, and partially from the Z is where that molecular orbital is coming from, and we end up with this right there. And so that's that 2A1 molecular orbital. We have this degenerate orbital right here, which is the two molecular orbitals of the same energy, which is the 1E right there. And so we see that this has that Y that PXY or that PY orbital from the nitrogen, and then the circles down here are the S orbitals from the hydrogens. And so then we have sort of the PX orbital up here at the top, and so we see how that is sort of bonding with these this s orbital right here. And so we see how that is sort of this px here sort of bonding with those two degenerate hydrogen group orbitals there, and then this sort of py here bonding with the degenerate s orbitals on the hydrogens right there. And so that's actually showing it right there, and we fill those with electrons. And we have this lone pair right here. So we see that that is very close to the energy of the 2pz, and so it's has very high non-bonding character to it, and so that's our lone pair. And so if you remember, the Lewis structure for ammonia is something that looks like this. So we have our three hydrogens bound to it, and then we have the lone pair, which is mostly coming from this 2pz atomic orbital right there. And so that is the nitrogen, and so this is kind of showing how we handle these E symmetries here. So the E symmetry on that gives us these sort of degenerate energy levels, but the E symmetries will always have these nodes going through them where there's the node between these sort of positive and negatively I almost said charge, but it's actually the positive and negative sign on our wave function. But anyway, that, like I said, is the ammonia. So we can do the same thing for the boron trifluoride, which has a D3H character or point group. And so here I'm just showing this is some of the ways you'll actually see the Lewis structure for boron trifluoride. So sometimes you'll see it like this. Sometimes you'll see it where they give it like this double bond here, and this will actually be shown oftentimes with resonance structures, and this is showing sort of that in these fluorides or these fluorines we have these lone pairs where this boron will have this this orbital right here that is unfilled, and so we see that these filled orbitals, the highest occupied molecular orbitals on the fluorines, are sort of sharing some of that their electrons with the empty orbital, the lowest unoccupied molecular orbital on the boron. But over here we see that this is kind of how we get the D3H symmetry by sort of thinking about it as this trigonal planar molecule. And so we actually end up with similar orbitals here because we have this E symmetry here. It's actually E prime because the prime is telling us that it is symmetric with respect to the reflection through the plane there. But it's still an E, so we still end up with these two degenerate energy levels here with the nodes between them. And so the other one is the A1 prime symmetry here, which is sort of like the A1 symmetry from above. But then we have the E prime here for our Y orbitals. And so that's another thing I guess I should point out is usually when we're doing these sort of trigonal kind of molecules like this, what you do is you have your sort of central atom here, and the axes you do on your sort of, I guess, B molecules or B atoms rather, you have the Y pointing in towards your central atom, then the X is sort of pointing, I guess, perpendicular to it, and then the Z would be sort of pointing up into the screen. And so that's kind of how we sort of label the axes on the sort of atoms coming off of these central atoms. So these would be the Y orbitals right here, sort of pointing in towards the central atom. These would be the X right here, where they're sort of perpendicular to the central atom, and these would be the Z right here, where they're sort of pointing up and down from the central atom. But we see these, the A1 prime and the E prime are sort of our main orbitals here. This E2 prime and E2 double prime only has some slightly bonding character here, and so we can actually look at these here. So we have our A1 prime here for the 2s and the 2py, and so those will group orbitals will form molecular orbitals with this A1 prime on our boron orbital, so our central atom orbitals there. These E primes here, so the E prime here for the Y and the E prime here for the X for our S orbitals, and we can see how those will form molecular orbitals with this E prime. So these two white ones here will form a bond with this white one here, where this dark one here with this dark one right here. And then the EX with this E prime, so we can see how this white one here will sort of bond with that white one there, and this dark one here can bond with that dark one there. Then the same for the 2py, where the white one here will bond with this white one here, this dark one with this dark one, this dark one here with this dark, and this light here with these two light right there. Then this figure is saying that there is a little bit of overlap with these two E primes right here for the px orbital, the 2px orbital. Then we have our 2pz here, so we have our A2 double prime. This will form sort of a partial bonding with this A2 double prime right here. So this is our molecular orbital diagram. So when we fill in the electrons here, so I put in green, so these are the bonding orbitals. This blue one here, this 1A2 double prime right here, which is going to this right there. So that is forming this bonding. Well, it's mostly non-bonding, but what's interesting about it is that it also forms this anti-bonding up here, which I have in purple. And so this is the lowest unoccupied molecular orbital. And so that is that sort of empty orbital here on the boron, which can act as an electron acceptor. And I'll actually talk about that in some future videos when I start talking about acids and bases and Lewis acids and Lewis bases and things like that. But so we have this A1 here, which is bonding. We have these two E prime here, which are bonding. So these two right here. This A2 double prime is mostly non-bonding, so this kind of makes it look like it's bonding, but this it's a little bit lower in energy than these other ones. So, and my inorganic chemistry textbook, the third edition by Miessler and Tarr, actually talks about how these sort of central molecular orbitals like this, so these ones like this, it's, you'll see those in sort of different orders in a lot of different places because the energy differences are so small between them that, like, it's kind of difficult to determine like which ones are actually higher and which ones are lower. And so, you see these kind of put in these different orders in different places a lot. But these are mostly non-bonding. And so that's why you'll see that, because it's one of those quantum mechanical things where, things don't have like sort of a definite, sort of position, or the sort of mixing of these orbitals. There's like partial mixing, there's partial overlap, and that's actually something I'll talk about a bit more in some future videos when I get into sort of the projection operators and coming up with these things. But for now, it's just we kind of have to accept that these sort of partial mixing and stuff like that ends up with kind of some weirdness going on with these non-bonding orbitals. But we do end up getting this up here, this anti-bonding orbital up here, this empty anti-bonding orbital, which can act as the lowest unoccupied molecular orbital. And so we'll actually see in sort of future videos down the line when I get into acids and bases that the Lewis acid is something that has this lowest unoccupied molecular orbital, and a Lewis base has this highest occupied molecular orbital that like to sort of bond together like this. And if you've taken organic chemistry, you've probably heard of like the nucleophiles and the electrophiles. So electrophile, so phile being sort of the Greek word for love, and so the this empty orbital here sort of loves electrons, so it is an electrophile, and these electrons here sort of love nuclei, and so those are nucleophiles. But anyway, I'm not going to get into that here. But anyway, I hope you found this video helpful. As usual, the lecture notes will be linked to in the description if you wanted to sort of look at this a little bit slower on your own. But anyway, I hope you found this video helpful, and I will see you in the next one.